Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll take a guided tour through AWS's broad and purpose-built database portfolio, covering everything from traditional relational databases and highly scalable NoSQL systems to specialized services for in-memory caching, time series data, analytics, and immutable ledgers. We'll explore how these offerings are designed to handle diverse workloads, deliver performance at scale, and integrate seamlessly across the AWS ecosystem to power modern, data-driven applications. Let's get started. Purpose-built databases are essential for meeting the unique demands of specific applications and workloads. These databases are optimized to handle particular types of data, offering superior performance compared to general-purpose databases. For example, time series databases are designed specifically to handle time-stamped data, such as sensor readings or logs, enabling faster and more efficient storage and retrieval of such data. One of the key advantages of purpose-built databases is their ability to offer scalability and flexibility. As business needs evolve, these databases can scale horizontally, making them ideal for handling large volumes of data. NoSQL databases, for instance, are well suited for managing unstructured or semi-structured data, providing flexibility in terms of schema and data models while also enabling growth. Data modeling is another area where purpose-built databases shine. For example, graph databases are specifically designed to store and query relationships between data points, making them particularly useful for applications like social networks, recommendation engines, and fraud detection. This tailored functionality allows these databases to solve complex problems that general-purpose databases might struggle with. These databases also provide better availability and fault tolerance. Many purpose-built databases are designed with high availability in mind, ensuring that even in the event of failures, the system can continue to operate. This is particularly important for mission-critical applications where downtime can have significant consequences. Purpose-built databases help speed up development processes as they provide the right tools and features for the task at hand. For instance, using a document database allows developers to store complex, hierarchical data structures easily without having to define rigid schemas, which accelerates development cycles. Overall, purpose-built databases enable organizations to achieve better performance, cost savings, and scalability, while simplifying development processes and ensuring that applications meet their specific data management requirements. AWS offers a broad spectrum of purpose-built database services, categorized by data models and optimized for specific application needs. This allows developers to select the most appropriate tool for the job rather than relying on a one-size-fits-all approach. Relational databases like Amazon RDS, Aurora, and Redshift are ideal for structured data and use cases requiring complex querying, transactions, and strong consistency. Key-value stores such as DynamoDB and Keyspaces offer fast, scalable access to simple data structures, making them well-suited for high-performance, low-latency workloads. In-memory databases like Elasticache and MemoryDB are designed for microsecond read-write access, commonly used in caching and real-time applications. Document databases such as DocumentDB support flexible, semi-structured data models like JSON, perfect for applications that require a dynamic schema. Graph databases, exemplified by Neptune, help uncover relationships and connections across data, ideal for social networks, recommendation engines, and fraud detection. Time series databases like TimeStream are purpose-built to efficiently handle timestamped data from IoT devices, logs, or monitoring systems. Ledger databases, such as Quantum Ledger Database (QLDB), provide immutable, cryptographically verifiable records for use cases like audit trails and financial systems. Finally, the Amazon Data Migration Service (DMS) supports seamless data transfer across these diverse systems, simplifying cloud adoption and modernization. Amazon RDS, which stands for Relational Database Service, is a fully managed cloud database solution from AWS that takes care of the heavy operational lifting so you can focus on building applications. Traditionally, managing a relational database meant handling everything from server provisioning and software patching to backups, monitoring, and scaling. With RDS, AWS abstracts all of that complexity by offering an out-of-the-box solution that automates these essential tasks. One of the biggest advantages of RDS is its simplicity. You can launch a production-ready database in minutes using the AWS Management Console, CLI, or SDKs. You're able to choose from multiple popular database engines, including MySQL, PostgreSQL, MariaDB, Oracle, and SQL Server, all without having to manually configure or maintain the underlying infrastructure. When it comes to scalability, RDS allows you to independently scale compute and storage resources. Whether your workload needs more CPU power or additional disk space, you can scale vertically with minimal downtime, helping you meet growing performance demands without service disruption. For mission-critical applications that require high availability and failover protection, RDS offers multi-AZ deployments. This means your primary database is automatically replicated to a standby instance in another availability zone. In the event of a failure, RDS automatically fails over to the standby with no manual intervention, minimizing downtime and maintaining business continuity. RDS also supports automated backups and manual snapshots. Backups are retained for a user-defined retention period and enable point-in-time recovery, ensuring that data loss is minimized in the event of an accident or issue. Snapshots can be created at any time and retained indefinitely for long-term archival. For performance tuning and optimization, RDS provides powerful tools like read replicas, which allow you to offload read-heavy traffic from the primary instance, improving throughput and scalability. You can also integrate your RDS environment with Amazon Elasticache to cache frequent queries, reducing latency even further. And with Performance Insights, you get a visual dashboard that shows exactly where your database load is coming from, helping you diagnose bottlenecks and optimize query performance over time. One of the strengths of Amazon RDS is its flexibility in supporting a broad set of database engines, giving you the freedom to choose the one that best fits your application's requirements. These engines fall into three main categories: commercial, open source, and Amazon native. Let's start with the commercial engines. Amazon RDS supports both Oracle and Microsoft SQL Server, two of the most widely used enterprise-grade database systems. These engines are well suited for organizations with existing investments in licensed software and legacy applications that rely on enterprise-specific features like Oracle RAC or SQL Server analysis services. RDS provides options for both bring your own license (BYO) and license included models, so you can match your licensing strategy to your operational needs. Next, we have the open source engines. RDS offers fully managed versions of MySQL, PostgreSQL, and MariaDB, the most popular open source relational databases. These engines are ideal for developers and startups looking for flexibility, community support, and cost effectiveness. PostgreSQL, in particular, is known for its advanced features like JSON-B support, window functions, and full-text search. MySQL and MariaDB are excellent for web-scale applications with high throughput requirements. With RDS, you benefit from the open source ecosystem while avoiding the operational overhead of self-management. And finally, the Amazon native engine, Amazon Aurora. Aurora is a purpose-built cloud-native relational database developed by AWS. It's available in two flavors, Aurora MySQL compatible and Aurora PostgreSQL compatible, offering up to 5x the performance of standard MySQL and 3x that of standard PostgreSQL, while maintaining compatibility with existing drivers and tools. Aurora offers features like distributed fault-tolerant storage, parallel query execution, and nearly instant failover, making it ideal for mission-critical, high-throughput workloads. And because it's a fully managed service built specifically for the cloud, Aurora provides seamless scalability, high availability, and global replication with minimal configuration. As you can see, Amazon RDS supports a diverse range of engines to meet various technical and business requirements. From open source databases for developer agility to commercial engines for enterprise-grade capabilities, and Aurora for those who need unmatched performance and availability in a cloud-native architecture. Amazon Aurora is not just another managed database. It's a cloud-native relational database engine that's been reimagined from the ground up to fully leverage the elasticity, resilience, and scalability of the cloud. It delivers the performance and availability you'd expect from high-end commercial databases like Oracle or SQL Server, but without the associated complexity, licensing headaches, or high cost. Built as part of the Amazon RDS ecosystem, Aurora gives you the best of both worlds. You get full compatibility with the tools, libraries, and drivers of MySQL and PostgreSQL, two of the most widely adopted open-source databases in the world, while benefiting from a massively improved underlying architecture. This compatibility makes it incredibly easy to lift and shift existing workloads, or even enhance legacy applications, with minimal changes to your application code or database schema. What truly sets Aurora apart is its modern, distributed architecture. Instead of relying on traditional monolithic storage systems, Aurora decouples compute from storage and uses a purpose-built, distributed, and log-structured storage engine. Your data is automatically replicated 6 ways across 3 physically separate availability zones in an AWS region, which means it's built for high availability and fault tolerance right out of the box, without you having to configure replication, failover, or backup schedules manually. The storage layer itself is fully managed and elastic. It grows automatically as your data grows, starting at just 10 gigabytes and scaling seamlessly up to 128 terabytes, so you never need to worry about pre-provisioning disk space or dealing with capacity constraints. That's a huge operational relief, especially for growing businesses or dynamic applications with unpredictable data patterns. Aurora is engineered for speed. It offers up to 5 times the throughput of standard MySQL and up to 3 times that of standard PostgreSQL, all while maintaining low latency even under heavy workloads. This makes it a go-to choice for mission-critical applications where performance and reliability are non-negotiable. Think e-commerce platforms, financial systems, SaaS backends, and enterprise workloads. Beyond performance and reliability, Aurora also offers powerful features to support modern development patterns and global scalability. You can scale reads horizontally with up to 15 low-latency read replicas. You can deploy globally distributed databases with Aurora Global Database for low-latency reads across continents. And for variable or unpredictable workloads, Aurora Serverless gives you the ability to scale compute capacity up or down automatically, helping you balance performance with cost efficiency. Amazon DynamoDB is a fully managed NoSQL database service designed for applications requiring low latency, high throughput access to data. It supports both key-value and document-based data models, making it versatile for a wide range of workloads. Built for seamless scalability, DynamoDB automatically distributes data across multiple partitions based on a hashed partition key, allowing it to handle millions of requests per second without manual sharding. By default, DynamoDB provides eventual consistency, but applications can opt for strongly consistent reads when needed. It also supports ACID transactions, enabling multi-item, multi-table operations with transactional guarantees. The service offers 2 pricing models: on-demand mode, which automatically scales throughput as needed, and provisioned capacity mode, where developers can allocate read and write capacity based on the workload to optimize costs. To enhance query flexibility, DynamoDB supports global secondary indexes, GSIs, and local secondary indexes, LSIs, allowing applications to efficiently retrieve data using alternative access patterns. Additionally, DynamoDB streams capture real-time changes to table data, enabling event-driven architectures by integrating with AWS Lambda, Amazon Kinesis, or other services for change data capture, CDC, auditing, and analytics. Security is a core aspect of DynamoDB, with built-in AWS Identity and Access Management integration, encryption at rest using AWS KMS, VPC endpoints, and CloudTrail logging for auditability. It also complies with industry standards such as SOC, HIPAA, PCI DSS, and FedRAMP, making it suitable for highly regulated environments. Overall, DynamoDB is a powerful solution for applications requiring millisecond latency, automatic scaling, and seamless integration with AWS services, making it a preferred choice for high-performance workloads such as gaming, IoT, e-commerce, and real-time analytics. Amazon Keyspaces is a fully managed, serverless database service that brings the power and flexibility of Apache Cassandra to the AWS cloud. If you've worked with Cassandra before, you know it offers excellent scalability and performance. but managing clusters, tuning throughput, and handling replication can quickly become operationally complex. Keyspaces removes that burden entirely. Amazon Keyspaces supports the Cassandra Query Language, or CQL, which means you can migrate existing Cassandra workloads or build new applications using familiar tools, libraries, and drivers, all without rewriting code. It's a drop-in solution that simplifies operations while maintaining compatibility with the Cassandra ecosystem. Designed from the ground up as a serverless service, Keyspaces automatically scales to meet your application's throughput and storage demands. There's no need to provision capacity or manage infrastructure. You just focus on your data model and queries, and Keyspaces handles the rest. This results in both consistent performance and cost efficiency, regardless of scale. Under the hood, it runs on AWS's highly resilient multi-AZ infrastructure. Data is automatically replicated across 3 availability zones within a region, providing built-in durability and fault tolerance. Whether you're supporting mission-critical enterprise applications or high-volume consumer workloads, Keyspaces delivers the availability and reliability you expect. And with its support for low-latency reads and writes, flexible schema design, and high write throughput, Amazon Keyspaces is ideal for use cases like time series data, IoT telemetry, real-time messaging, and recommendation engines. In-memory caching solutions have become a foundational component of modern application architectures due to the growing need for speed, scalability, and real-time responsiveness. Applications today, particularly those in e-commerce, gaming, ad tech, and financial services, often require ultra-low latency, where even a few milliseconds of delay can impact user experience or revenue. Traditional storage systems, including those using SSDs, are simply not fast enough to meet these sub-millisecond performance requirements. In-memory caches like Amazon ElastiCache are designed to handle millions of operations per second, enabling high-throughput access to data and alleviating performance pressure on back-end databases. By caching frequently accessed or computationally expensive data, these systems reduce the load on primary data stores, helping improve database performance, lower operational costs, and ensure scalability as the application grows. They also play a critical role in improving application resilience. During database slowdowns or outages, cached data can keep core functionality running, providing a safety net and maintaining user experience. This is especially valuable in globally distributed or high availability environments. In-memory caches are also essential for personalized and dynamic content delivery. User sessions, preferences, and tokens can be stored and accessed in real time, allowing applications to deliver contextual responses with minimal delay. For applications with complex queries, such as joins or aggregations, caches can store pre-computed or previously fetched results, significantly reducing query latency and computational overhead. Additionally, many use cases involve ephemeral or time-sensitive data, such as rate limiting, real-time scoring, or CAPTCHA validation. These don't need persistent storage, but require fast access and automatic expiry, which are strengths of in-memory systems. Finally, as microservices and distributed systems become the norm, in-memory caches serve as lightweight shared layers for coordination, whether as a session store, pub/sub messaging bus, or a mechanism for distributed locking. In all these scenarios, in-memory caching plays a pivotal role in delivering scalable, fast, and resilient application architectures. Amazon ElastiCache is a fully managed, low-latency, in-memory data store and caching service that supports 2 popular open-source engines, Redis and Memcached. It is purpose-built to power high-throughput, real-time applications by reducing data access latency to microseconds and enabling applications to scale seamlessly with minimal operational overhead. At its core, ElastiCache allows you to offload frequently accessed or transient data from slower back-end data stores, such as relational or NoSQL databases. This improves overall application performance and reduces load on primary databases, often resulting in significant cost savings. Whether you're dealing with high-volume transactional systems, low-latency microservices, or event-driven architectures, ElastiCache can act as a vital acceleration layer. For Redis, ElastiCache offers advanced capabilities such as cluster mode for horizontal partitioning, read replicas for scaling read throughput, and multi-AZ with automatic failover for high availability. It also provides daily backups, point-in-time recovery, and encryption in transit and at rest to meet enterprise-grade security and compliance requirements. For memcached users, Elasticache delivers a simple, high-speed caching layer with a multi-threaded architecture and automatic node discovery. Elasticache is ideal for a wide range of use cases, such as session management, real-time analytics, leaderboards, API response caching, and pub/sub messaging systems. Its flexibility, performance, and seamless integration make it a foundational component for building modern, cloud-native applications that demand speed, scalability, and reliability. Amazon MemoryDB is a fully managed, Redis-compatible, in-memory database service designed to deliver ultra-fast performance with microsecond read and low millisecond write latencies. It's built from the ground up to support real-time applications that demand high throughput, low latency, and high availability, all without the heavy lifting of managing infrastructure. One of the key advantages of MemoryDB is its full compatibility with open-source Redis. Developers already familiar with Redis commands, data types, and client libraries can continue using the tools they know and love without having to re-architect or refactor application code. Unlike traditional in-memory caches that are often ephemeral and used as secondary data stores, MemoryDB is designed for durability. It provides multi-AZ replication, storing data redundantly across multiple availability zones to protect against node and zone failures. MemoryDB is particularly well suited for real-time applications. Think of use cases like gaming leaderboards, financial transaction scoring, e-commerce personalization, session management, or IoT device state tracking, applications where milliseconds matter. Its in-memory architecture ensures responses are delivered at lightning speed, giving users a seamless, responsive experience. The service also offers strong eventual consistency. Unlike typical caching layers, MemoryDB uses a durable transactional log to persist changes, ensuring that data is not only fast, but reliably stored and recoverable. When it comes to scaling, MemoryDB is built to handle it effortlessly. It supports horizontal scaling through sharding, letting you distribute data across multiple nodes, and vertical scaling by adjusting node sizes to meet your application's demand. In summary, Amazon MemoryDB delivers the performance of an in-memory database, the durability of a multi-AZ architecture, and the familiarity of Redis, all in a managed, secure, and scalable package. In today's application landscape, flexibility and speed are critical. Traditional relational databases can be limiting when dealing with dynamic, fast-changing data models. This is where document databases come in. They provide the agility needed to support modern development patterns. One of the biggest drivers for adopting document databases is the ability to work with flexible and evolving schemas. Unlike relational systems that require predefined structures, document databases allow data to be stored without rigid schema enforcement. This makes it much easier to adapt your data model as your application evolves, without costly refactoring or downtime. Document databases also align naturally with JSON, which is the de facto standard for modern APIs and microservices. Whether you're building RESTful services or interacting with front-end frameworks like React or Angular, your data is often already in JSON. Document databases allow you to store and query that data directly without needing to flatten or transform it. Because of this model, document databases are particularly well suited for semi-structured or hierarchical data, like user profiles, product catalogs, or IoT telemetry, all of which may have optional or nested fields. Another advantage is simplified data representation. In a relational world, representing a real-world object like a customer order might require multiple join tables. In a document database, all relevant data, customer info, order details, shipping address, can live in a single document. This not only mirrors the object structures in your code, but also improves performance by reducing the number of queries needed to retrieve related data. Teams also benefit from faster development cycles. Without the overhead of schema migrations or join management, developers can move quickly, iterate on data models, and prototype features faster, which is crucial in agile environments. From a performance standpoint, read operations become more efficient, especially when accessing aggregated or nested data. Since related data is stored together, your app can fetch everything it needs in a single query, improving latency and reducing load. Finally, document databases are a great fit for microservices and event-driven architectures. Each service can have its own data model, often best expressed as a document. This decoupling promotes autonomy and makes services easier to develop and deploy independently. Amazon Document DB is a fully managed document database service designed specifically for storing, querying, and indexing JSON data. It's a great fit for modern applications that use semi-structured or document-based data models. Amazon Document DB serves as a drop-in replacement for MongoDB, enabling applications to connect and operate using the same MongoDB drivers and APIs with little to no changes, making migration fast, simple, and low risk. What makes Amazon Document DB particularly attractive is its MongoDB API compatibility, which means it supports the same core MongoDB APIs, query language, and data model. This compatibility allows teams to migrate existing MongoDB workloads to DocumentDB with minimal code changes. In many cases, applications can connect using the same MongoDB drivers, libraries, and tools they're already using. As a result, teams can retain their development workflows, reuse existing queries, and avoid costly re-architecture efforts, making the transition to a fully managed, scalable document database service both seamless and cost-effective. Under the hood, DocumentDB is built on a purpose-engineered architecture that separates compute and storage, allowing each to scale independently. The storage layer is automatically replicated across 3 availability zones and can grow up to 128 terabytes per cluster, all without requiring manual sharding or downtime. In terms of functionality, DocumentDB offers rich query support, allowing developers to run complex queries against deeply nested JSON documents. It also supports aggregation pipelines and ACID transactions, which are essential for maintaining consistency in critical workloads. Because it's fully managed by AWS, teams don't have to worry about provisioning infrastructure, patching, or backups. DocumentDB provides automatic backups, point-in-time recovery, and multi-AZ high availability, making it resilient to failures and well-suited for mission-critical applications. Finally, for applications that are read-heavy, DocumentDB allows you to scale out read operations using up to 15 low-latency replicas, improving query throughput and overall performance. In today's data-driven world, many of the most valuable insights come not just from the data itself, but from how that data is connected. Traditional relational databases and even document stores often fall short when it comes to modeling and querying complex relationships at scale. As relationships deepen and grow in complexity, operations like multi-table joins or nested queries become increasingly expensive and inflexible. Graph databases were designed from the ground up to address these limitations. They model data as nodes and relationships, allowing for index-free adjacency, meaning each node directly references its connected nodes. This enables constant time traversal, even across massive networks, making graph databases uniquely capable of handling use cases that involve rich interconnections. One of the biggest advantages of graph databases is their flexible schema. Unlike relational databases that require a rigid structure, graph models can evolve naturally as new entity types or relationships are added. This agility is crucial for modern applications that demand rapid iteration and constant evolution. Graph databases are particularly powerful for real-time querying of multi-hop relationships. Whether it's identifying fraudulent transaction patterns, surfacing personalized content recommendations, or tracing supply chain disruptions, these queries can be executed in milliseconds thanks to the graph model. Furthermore, as AI and machine learning become more integrated into analytics pipelines, the contextual richness of graph data offers a new dimension of features, such as node embeddings and relationship patterns, that boost model accuracy for tasks like fraud detection and entity resolution. From financial services and healthcare to media, telecom, and cybersecurity, graph databases are being adopted to uncover hidden patterns, improve personalization, and derive deeper, more actionable insights. Insights that simply aren't possible with traditional databases. Amazon Neptune is a fully managed, purpose-built graph database service designed to efficiently store and query highly connected datasets. It supports both major graph models, Property Graph and RDF, Resource Description Framework, making it a versatile choice for a wide range of applications. Developers can use industry-standard query languages such as Gremlin for property graph traversal and Sparkle for semantic queries, providing flexibility based on the nature of the data and use case. Neptune is optimized for high performance with index-free adjacency, allowing it to execute deep and complex graph queries with extremely low latency, even across billions of relationships. It's ideal for scenarios where relationships between entities are central to the problem domain, such as social graphs, recommendation systems, or knowledge graphs. As a fully managed AWS service, Neptune handles the heavy lifting of database maintenance. It offers built-in high availability across multiple availability zones, supports automatic backups and snapshots, and enables point-in-time recovery to protect against data loss. Monitoring and access control are tightly integrated with Amazon CloudWatch and AWS IAM, providing enterprise-grade observability and security. Neptune's architecture is designed for durability and scalability. Built on the Amazon Aurora storage engine, it decouples storage and compute, allowing the database to scale seamlessly as data volumes grow. It also supports read replicas, enabling horizontal scaling of read throughput to meet high-demand workloads. Crucially, Amazon Neptune supports full transaction semantics for highly concurrent OLTP workloads. It is ACID compliant, ensuring immediate consistency and reliable execution of transactional operations, making it not only fast, but also trustworthy for mission-critical applications. As modern systems become increasingly connected and instrumented, applications in domains like IoT, DevOps monitoring, application telemetry, and real-time analytics are generating massive volumes of high-frequency, time-stamped data. These workloads are characterized by continuous data streams that require high-throughput ingestion and low-latency processing, challenges that can quickly outpace the capabilities of traditional general-purpose databases. The core limitation is that relational databases weren't built with time as a central dimension. They treat timestamps like any other column, which makes time-centric operations like sorting by time, querying within specific intervals, or performing rolling aggregations inefficient and cumbersome. In contrast, purpose-built time series databases like Amazon TimeStream are designed from the ground up with time as a first-class citizen, optimizing for both storage and query patterns that revolve around temporal data. Time series workloads also demand specialized query capabilities that go beyond basic filtering. These include rolling window aggregations, downsampling for dashboards, computing derivatives to spot trends, and even interpolating missing values. In a general-purpose database, these queries often involve complex joins, subqueries, and custom logic, whereas time series databases support them natively and efficiently. Another key factor is data lifecycle management. Time series data tends to lose value over time. For example, last-minute CPU usage is far more relevant than what it was a month ago. Time series databases recognize this pattern and provide built-in lifecycle policies that can automatically tier data from fast in-memory storage to lower-cost archival tiers, or expire it altogether, without manual intervention. Finally, time series data usually has a predictable schema and structure, repeating measurements from the same sensors, services, or systems. This makes it ideal for advanced compression and columnar storage techniques, enabling better performance and lower storage costs at petabyte scale. All of these reasons make a strong case for adopting a purpose-built time series database when working with workloads where time is the dominant dimension. Amazon TimeStream is a fully managed, purpose-built time series database designed specifically for handling the scale, speed, and complexity of time-stamped data. Whether you're building large-scale IoT solutions, monitoring your cloud infrastructure, or capturing application telemetry, TimeStream offers a high-performance, cost-effective, and operationally simple platform to ingest, store, and analyze time series data. One of the core strengths of TimeStream is that it's entirely serverless. That means there's no infrastructure to provision, manage, or scale. AWS handles everything, from automatic scaling, high availability, and replication, to patching and maintenance, so your teams can spend less time on DevOps and more time delivering insights and features. A major differentiator is TimeStream's automated data lifecycle management. You can configure retention policies that automatically tier data, keeping recent data in memory for low latency access, while older data is seamlessly migrated to magnetic storage for long-term retention at significantly lower cost. This approach ensures that your queries are always fast and cost-efficient, no matter the age of the data. At its core, TimeStream provides a powerful SQL-based query engine that's optimized for time series operations. It supports advanced functions like rolling aggregations, interpolation, rate of change calculations, and time window filters, enabling developers and analysts to express complex temporal logic with simple, readable syntax. Under the hood, TimeStream is engineered for high performance and scale. It can handle millions of writes per second, while supporting sub-second query latency, even when working with billions of data points. This makes it suitable for everything from real-time monitoring dashboards to historical trend analysis and machine learning feature extraction. Amazon TimeStream provides the right combination of speed, scalability, cost efficiency, and ease of use for modern time series workloads, without the operational burden of managing infrastructure or databases. In today's digital-first landscape, businesses generate and depend on massive volumes of transactional data, from supply chain events and financial operations to contracts, compliance records, and more. But with that reliance comes a fundamental challenge. How do we ensure that this data remains accurate, traceable, and tamper-evident over time? Traditional relational databases are optimized for flexibility, performance, and ease of access, but they weren't designed to preserve a trustworthy history of changes. Once a row is updated, the original value is overwritten, and unless custom audit logic is built in, that history is lost. This creates a serious gap in data lineage, which is the ability to trace the origin, transformation, and movement of data throughout its lifecycle. At the same time, regulatory and compliance pressures are intensifying across nearly every industry. Auditors, regulators, and even business partners increasingly demand systems that can demonstrate data integrity. Not just that data is present, but that it hasn't been manipulated. To meet these expectations, many teams resort to building complex audit trails and change tracking systems from scratch. These homegrown solutions are often inconsistent, difficult to maintain, and fragile in the face of evolving business needs. Reconciling data across siloed systems becomes a manual, time-consuming process, prone to errors and delays. Blockchain emerged as a promising alternative, offering cryptographic immutability and distributed trust. But in many enterprise contexts, blockchain's overhead, including consensus algorithms, decentralized management, and token governance, outweighs the benefits. What organizations really need is a centralized, cryptographically verifiable ledger that's simple to manage, scalable, and easy to integrate with modern applications. That's the heart of the modern ledger challenge, and it's exactly what Amazon QLDB was built to solve. Amazon QLDB, or Quantum Ledger Database, is a fully managed ledger database service designed to provide a transparent, immutable, and cryptographically verifiable transaction history. Unlike traditional databases that overwrite data with each update, QLDB maintains a complete, append-only journal of every change, giving you a reliable, auditable trail of all activity over time. What makes QLDB truly powerful is its immutability at the core. Once a transaction is committed to the journal, it cannot be modified or deleted. This ensures that your data history is preserved exactly as it happened, perfect for use cases where trust, accountability, and traceability are paramount. But QLDB doesn't stop at just immutability. It adds cryptographic verification to the mix. The service uses SHA-256 hashing to chain each transaction to the one before it, allowing you to prove, mathematically, that the history hasn't been altered. This means you don't just store the past, you can defend it. QLDB also stands out for its developer-friendly approach. It supports PartyQL, a SQL-compatible query language that works across structured and semi-structured data. With PartyQL, you can query both the current state of your data and the full history with ease. No need to learn a new paradigm or dig through raw logs. The database uses a document-oriented data model, allowing for flexible JSON-style data representation that adapts well to evolving schemas. This makes it a great fit for dynamic applications that require structure but not rigid tabular models. And unlike blockchain-based solutions, QLDB doesn't require distributed consensus, mining, or token management. As a result, it offers 2 to 3 times better performance for centralized use cases, without the complexity and operational burden of a decentralized network. Amazon Web Services offers a comprehensive suite of analytics database services, each purpose-built to address specific needs across the modern data lifecycle, from storage and processing to querying and visualization. Let's start with Amazon Redshift, AWS's fully managed petabyte-scale data warehouse. Redshift is designed for high-performance analytical workloads and supports standard SQL, columnar storage, and massively parallel processing. It's ideal for structured, OLAP-style queries and powers dashboards, reports, and complex aggregations at scale. Next, we have Amazon Athena, a serverless, pay-as-you-go query engine that lets you analyze data directly in Amazon S3 using standard SQL. There's no infrastructure to manage, making Athena perfect for quick ad hoc querying of structured, semi-structured, or even unstructured datasets, like logs, clickstreams, or CSV files. For search and observability use cases, Amazon OpenSearch Service provides a scalable, fully managed platform based on Elasticsearch. It enables full-text search, log analytics, and real-time dashboards, often used for monitoring applications, detecting anomalies, or powering search experiences. Amazon EMR, or Elastic MapReduce, is AWS's managed big data platform for running open-source tools like Apache Spark, Hive, and Presto. EMR is ideal for large-scale ETL, machine learning preprocessing, and complex custom analytics that benefit from distributed computing. Amazon S3 combined with lake formation forms the foundation for building secure and scalable data lakes. Lake formation adds governance, access control, and security policies, enabling consistent management across diverse analytics tools. Finally, on the front end, Amazon QuickSight provides business intelligence at scale. It enables users to create rich, interactive dashboards and perform visual analysis with built-in ML insights. QuickSight integrates natively with Redshift, Athena, and other AWS sources to make data consumption seamless for business users. With a wide range of database options available, selecting the right one is critical to application performance, scalability, and cost efficiency. AWS offers purpose-built databases optimized for specific data models and access patterns. Understand data structure. The first step in choosing the right database is understanding the structure of your data. If your data is highly structured, relational databases may be ideal. If it's unstructured or semi-structured, you might consider NoSQL options like document, key value, or graph databases. Performance and speed. Consider the performance requirements of your application. In-memory databases are suited for real-time applications where low latency is critical, while time series databases excel at handling large volumes of timestamped data with fast read and write operations. Scalability needs. Think about your application's growth over time. NoSQL databases offer horizontal scalability, making them a good choice for applications that need to handle large volumes of data or scale quickly. In contrast, relational databases often scale vertically and may be more suitable for applications with more static data requirements. Consistency and availability. Determine the level of consistency and availability required by your application. If ACID compliance, atomicity, consistency, isolation, durability is essential, a relational database or NoSQL database might be the right choice. If the application can tolerate some inconsistency for the sake of availability, a NoSQL database with eventual consistency might be more appropriate. Data relationships. Consider the complexity of the relationships between your data. If your data model involves complex interrelated data, graph databases are ideal for representing and querying such relationships. For simpler, tabular data, a relational database may suffice. Querying requirements. Think about the types of queries you need to perform. If your queries are complex and involve join operations, a relational database may be the best choice. However, if your queries are more flexible and involve large amounts of unstructured data, NoSQL databases like document stores might be more suitable. Security and compliance. Make sure the database you choose meets your security and compliance needs. For industries with strict regulations, ensure the database supports the necessary encryption, authentication, and auditing features required to meet legal and regulatory standards. Cost and maintenance. Consider the total cost of ownership, including both infrastructure and ongoing maintenance. Cloud-based databases offer managed services that reduce the operational overhead, while self-hosted databases might give you more control but require more effort in terms of updates, backups, and scaling. By aligning your workload characteristics with the strengths of each database type, you can maximize performance, reduce operational complexity, and build more resilient and scalable applications. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.